let's get going on today's journal entry. I want to look at the graph of f of x equals x to the fourth minus 8x squared plus 2. And I want to first, let's look at this on the calculator because I think there's some really good information available to us if we explore the graph. So let me get my calculator up there. I'm going to do this with my 84. So we're going to type in the function x to the fourth power minus 8x squared plus 2. Let's graph that. Let's see, let's get a window so that we can see the whole graph. So I'm going to zoom standard. There's my graph. That's pretty good. I'd like to see the complete graph. The graph seems to extend below the screen. So I need to go lower down on the y values, let's say to negative 15. Let's see if that works, and that seems to work. Now, as calculus students, we've had a lot of conversations about finding a relative maximum point, right? We would look at the derivative, we look for the derivative to change from positive to negative, and we can find the relative maximum, and it's a really careful choice of words. Relative maximum. This isn't the highest point on the graph. This is just locally. If you look in a small neighborhood, this is the maximum point because the graph changes from increasing to decreasing. We also have relative minimum points. Relative max, relative mins. But if I wanted to have a conversation about absolute max, what is the absolute highest point on the graph? Well, this graph extends forever in both directions. It heads off to infinity. So some textbooks would say there is no absolute maximum. It just goes on forever and ever and ever. Some books say the absolute maximum is positive infinity. Great. What I want to do is I want to talk about absolute extrema. So absolute max and absolute mins on an interval. So here's what I want to do. I want to look at the graph of x to the fourth minus 8x squared plus 2 on the interval negative 3 to 1. So let's change our window. X min, negative 3. X max, positive 1. Let's graph it, and let's have a conversation now about absolute max and absolute min. If I only consider the part of the graph from negative 3 to positive 1, I still have a relative maximum. My graph changes from increasing to decreasing. I still have a relative minimum. My graph changes from decreasing to increasing. But I actually have an absolute maximum, and the absolute maximum point is here at the endpoint. So, let's recap that. We have a relative maximum, we have a relative minimum, we have an absolute maximum point. Do we have an absolute minimum? Is there a point on the graph that is lower than any of the other ones on the interval? Yes, we do. It's over here at the relative minimum. Sometimes that's going to happen. So that is absolute max, absolute min, relative max, relative min. With the graph in front of you, what I want to do now is spend a little bit of time on the calculus so we can go through how do you properly show absolute extrema without using the graphing calculator. So, let me zoom out. Ooh, wrong way. To find absolute extrema, there's a process that we're going to go through, and it's going to be the same process again and again. I want to find the absolute extrema on the interval negative 3 to 1. So first of all, we're going to find relative extrema. What do I mean by that? I mean relative max and relative min. Well, how do we go about doing that? We are going to take a derivative. We're really good at taking derivatives now. Derivative of x to the fourth minus 8x squared plus 2 is 4x cubed minus 16x. Didn't need anything but the power rule. We're going to factor 4x cubed minus 16x, I can factor out 4x, leaving me x squared minus 4. I can reduce that x squared minus 4 as x plus 2 and x minus 2. I set my derivative equal to 0. That means x equals 0, x equals negative 2, or x equals positive 2. Took the derivative, I set it equal to 0. I found my critical points. At all three of these points, the first derivative will be equal to 0. We're going to construct our number line test. This is a number line for f prime. And I know that at 0, at negative 2, and positive 2, the derivative is equal to 0. I have horizontal tangent lines. I don't know for sure where I have a relative max or a relative minimum. So our next move is to select your test values. So we pick a point to the right of 2. I'm going to go with x equals 3. I'm going to pick a point between 0 and 2. Let's be kind. Let's say x equals 1. Between negative 2 and 0, we pick negative 1. And to the left of negative 2, say we pick negative 3. You know what we're going to do next. We're going to take each of these 4 test values and we're going to plug them into the derivative. Now, you can go with this version of the derivative, that version of the derivative, or this one. I always like the factored form. That one seems to work best. So let's see. If x equals negative 3, 4 times negative 3 is a negative number, not negative 1. Sorry. It's a negative number. Negative 3 plus 2 is a negative number. Negative 3 minus 2 is negative. So for my test value of x equals negative 3, negative times negative times negative is negative. So I expect that for all values of x to the left of negative 2, I'm going to get negatives. Now I pick between negative 2 and 0. We said x equals negative 1. Go back to your derivative. Plug it in. You get a negative number, a positive number, a negative. Negative times negative is positive. So the derivative is positive in that interval. We select a value between 0 and 2. We said x equals 1. We plug it in. A positive number, a negative number. God, I keep writing negative 1. It's just a negative number. Positive times positive times positive. Positive times positive times negative is negative. So, negative on that interval. X equals 3 is my test value. Plug it in. I get 4 times 3 is 12. All I care about is positive. 3 plus 2 is 5. Again, positive. 3 minus 2 is 1. Positive. Positive times positive times positive is positive. So, we've done our number line test. We know we can with confidence say that we have a relative minimum at x equals negative 2 because f prime changes from negative to positive. We have a relative max at x equals 0 because f prime changes from positive to negative, and we have a relative min at x equals 2 because f prime changes from negative to positive. Those are all things that we confirmed through our graph, but now we know for sure using the calculus. Okay? Those are your relative extrema. The second thing I want to do is I want to look at the interval I'm interested in. I'm only interested in looking at the graph from negative 3 to positive 1. So when I look at my number line, I don't actually care what happens to the graph before negative 3, so we throw all that out. We don't care what happens to the graph after x equals 1. That's not in the interval I'm interested in. So just between negative 3 and 1, On that interval, I have a relative min at -2. I have a relative max at 0. And this guy down here, where we said relative min at 2 is true, but it's not important. Okay? The second step is, now that we've established our extrema within the proper interval, the second thing is we want to evaluate the function at the extrema and at the endpoints. Okay? So what do I mean by that? I mean, I want to find f of -2. I want to find f of 0 because those are my extrema, but I'm also going to evaluate my function at -3. Sorry, let me scoot that up. And I want to evaluate my function at +1. So we're going to go back. This is f. This is not the derivative. Go back to the original function and replace all the x values with -2. -2 to the 4th minus 8 times -2 squared plus 2. -2 to the 4th is 16. -2 squared is 4. -8 times that, -32 plus 2, and we should get -14. f of 0, this should be easier. 0 to the 4th minus 8 times 0 squared plus 2. 0 minus 0 plus 2 is 2. Evaluate the function at -3. -3 to the 4th minus 8 times -3 squared plus 2. -3 to the 4th is 81 minus 72 plus 2. I get 11. f of 1, 1 to the 4th power minus 8 times 1 squared plus 2. 1 minus 8 plus 2, what is that? -5. These values that I just found are the y coordinates. When x equals -2, y is -14. When x equals 0, y is 2. When x equals -3, y is 11. When x equals 1, y is -5. If I want absolute extrema, where do I see the absolute maximum point? And I have an absolute maximum value, given these four choices. Absolute maximum value is 11, which occurs at x equals -3. If I want an absolute minimum value is, look at the 4, which one is the lowest? Absolute minimum value is -14, which occurs at x equals -2. So, to conclude, the first step was we looked at our function. We wanted absolute extrema on that interval. So we took a derivative. We did the number line test to find our relative extrema. That was the first step. The second step is we evaluated our function at our extrema, relative extrema, plus the endpoints. You must check the function at the endpoints. And then lastly, we drew our conclusion. We found our absolute maximum value to be 11, and that happened at -3. We found our absolute minimum value to be -14, and that occurred at -2. And lo and behold, if we go back to the graph, that should match our findings exactly. When I evaluate the function at -3, I get +11. When I evaluate the function at -2, I get -14. Wow! Bravo! Now, the good news is the practice problems you're going to do today have nothing to do with absolute extrema. This was just an idea that I wanted to plant in your brains now to make it a little easier for when we come back up with this idea next week. Good luck with the practice problems, and I'll see you guys on Monday.